In this video, we'll take a deeper look at the related rate problems. These are applications of derivatives, and we could honestly spend a month looking at all different types of examples, looking into deeper, harder, more complicated situations, but we're going to kind of stick with some basics. The basic idea of a related rate problem is that any type of a situation, if regular variables are related, meaning that there's some equation that relates to them, that connects them, so if those variables are related, their rates of change, hence their derivatives, are also related. And by related, I still mean that same thing. If the regular variables are in an equation together, then their derivatives will also be in an equation together. And the way we'll get that derivative equation is by implicitly taking the derivative of the first equation. So that's what I was trying to explain in my notes, and I think Dr. Bob does a decent job of that as well. But let's try and say that again. So anytime we see one of these word problems and we're being given information about a situation and we know about how something is something is moving, how something is changing, and we're being asked about how something else changes, that is a related rate problem. So the basic setup for that is try and draw a picture if necessary. Let's identify all the variables. What are the quantities that are actually changing in the problem? Let's find any of the given information. If we know how some of those things are changing, those would be derivatives we already know. And then what are they asking us for? What quantity rate of change are they interested in? That's the derivative we're trying to find. So after we have all that laid out, if we weren't given an equation that relates the variables, we'll get one ourselves. Sometimes those equations will be given. Sometimes it'll be something like how volume of a cylinder relates volume, radius, and height. Volume of a box equals length times width times height. So those quantities are related. We'll see several right triangle situations that come up. The lengths of a side in a right triangle are all related through Pythagorean theorem. A squared plus b squared equals c squared. If we're curious about how an angle is changing with respect to a side, we'll still draw a right triangle, but then we'd use a trig function. So there's a lot of things to look at, but getting through a few basic examples and getting some experience is really the way to go here. So I'm going to take one of the examples I gave you in my notes. I gave you the equation x cubed minus 3xy squared equals 2y plus 4. We were given this equation and we were told find dx dt at the point 2 comma negative 1 given dy over dt equals 3 units per second. This is a super basic generic. We're going to look at some more specific applications with some very specific purposes. This is a very, very generic one, and this is incredibly similar to the first video link that I posted, Related Rate Problem 1, which was made by Dr. Chu, and he describes almost this exact same situation. He gives you a little extra background, though. But this is the same way we should think about it. We've got some graph. That's what this equation gives us. He actually had a nice graph drawn for his. I have no idea what this looks like, so I'm just going to draw something. So I'm just going to pretend for a moment that I've got some graph, and whatever that function is doing, just one second. So whatever that function is doing, there's some function. I'm sorry, it's not a function. There's a graph that could go with that equation. And the way to think about this, let's pretend that an ant or some object is walking along this path. So as they're doing this, they're not just moving left, right, or up, down. They're moving in both directions. As they're along this part, if they're going in this direction, they're going both right and up. But now I'm circling. Now I'm going up and then left, and now left and down. So I'm getting components of left, right, and up, down all at the same time. So what we're supposed to understand here is that this is the path that something is moving. And the idea of dy dt is 3 units per second means as my object is passing through this particular point, the point that was given here, that its y component, its direction, is positive 3 units per second. So in 1 second, it's jumping up 3 units. But it doesn't go straight up, it's got to go to the right as well. So as it's going up at that rate, how fast did it have to go right to balance that out? That's the real full understanding of this problem, and that's why I think Dr. Chu's video is a very good one to follow, because he gives a lot more understanding, but this also serves as a very basic problem to get us going. We want to know this derivative while knowing this one. Well, that means we need to know something about the regular variables x and y, some relation that connects them. Here it is. There's the equation, and that was given in this problem. But we've got the equation that connects x's and y. I need the equation that connects dx dt and dy dt. And the way I will find that equation is by taking the derivative with respect to time. All these are with respect to time here. So I will take that derivative with respect to time of that original equation. This is an implicit derivative. You could follow my notes, everybody, because that's exactly what I'm doing here. If you just take this derivative with respect to t, well, nothing fancy here. That'll give me a 3x squared, but it has to get marked dx dt. This is where I warned you in Dr. Bob's videos. He used to just use the y prime notation when it was dy dx, but now we really need to embrace the Leibniz notation because there are no t's here, so everything needs this extra marking. And just marking it x prime and y prime can get a little messy. So you can make it work, but it's just a little better to do it this way. So I took the derivative of this piece and it was marked. And that also is what he was talking about when he said chain rule. Technically, we took the derivative of x cubed, and the derivative of the inner part is taking the derivative of x. But we don't need to think of that as chain rule. We had plenty of understanding there, just to realize that's what he was talking about. So I took this derivative and it got marked. Now I need some product rule. Derivative of the first times plain old second plus derivative of the second times plain old first. Both of those derivatives, here I was taking derivative of an x. There's no x left, but it's still marked dx dt. Even though these are related rates, these are still very good practice problems taking implicit derivatives. So over here, now I'm taking the derivative of the second part. So the derivative of the y squared gives me the 2y dy dt. Again, that's where the marking happens. And there's the plain original first equals, the other side is more simple, so I just get a 2 dy over dt. Now we'd go back. I mean, some people already want to manipulate their equation in some sense, but now basically all I'm doing from here, I want dx dt, so there is my unknown. Doesn't matter if there's two of them. After we plug in, these will end up being like terms. Well, I also have dy dt, so if I'm going to find this, I could only have one unknown, so it means I'm going to need a value for this, and that's exactly what we have here, so we plug that in for dy dt. But I still have variables x and y. Well, I have this point. And that's the last trick, everybody. In related rate problems, this object keeps moving around the circle, or some of the other problems we'll see. The picture keeps changing, but we very often need to identify what moment we care about. Sometimes that moment is given to us by time, how much time has passed, but here the moment is given by the x and y values. So now I'm able to plug everything in and continue to solve, and this is going back to the notes. I plugged everything in right here, cleaned some things up, still had multiple dx dt's, but now I'm able to combine them, just like 12x minus 3x is 9x. Same thing with the dx dt's. Everything else is no more variables, so I was just able to solve. The last thing to realize here, some units. This was a generic problem, but dy dt was measured in units per second, so is dx dt. I mean, I reduced the fraction. Why is this negative? Well, at that moment, while y was pushing up, x needed to actually push to the left. So there still is some understanding of the signs, the plus or minus that go with these. So that's just the first one. I hope this explanation helps so you can get back into this one. And again, also use Dr. Chu's video in that first related rate problem. But let's go right into the second one as well. This next problem that I gave you has this more generic situation, and this is exactly what's in Dr. Bob's basic video. He does almost the same thing. You throw a rock into a pond, and when you throw the rock in, you get this growing ring of circles, right? You throw a rock into the pond, you get a small little circle, but that circle just keeps waving away further, so you get this growing ring of circles. The radius of that pond is growing at this rate. Hey, that's a rate. Even just from the units, we need to start identifying, well, that is a derivative. Well, if the radius grows at that rate, that's a little more natural that we will label as dr dt, the derivative of the radius with respect to time. So we know the derivative of the radius. We know dr dt. At what rate is the area of the circle growing when the radius is 20 centimeters? We know dr dt, we want to find dA dt. We're not being asked what is the area, we're being asked what rate is the area growing. So I have a lot more written out that we kind of just discussed a little bit. I drew a picture first, just drawing my growing ring of circles, just to try and get a little visual. The area of the circle and the radius drawn out. And again, this picture keeps changing. We know how the radius changes, so I'll label that dr dt. The fact that it's growing is a good reason to keep this positive. We do want to take advantage of the sign when it can be helpful. And we want to know how the area grows. We know dr dt, we want to find dA dt. Well, what's an equation that connects regular A and regular R? Well, we're talking about circles. So area is pi r squared. There's the connection. There's the relation between the regular variables. Now I'll take the derivative. Nothing fancy here. Don't let the pi fool you. Pi's not a variable. It's just like if it was 4r squared, the derivative would be 8r dr dt. So I just still took that derivative in the same way. And now we'll plug in what we know. We want dA dt. So that means we need to have a value for r and dr dt. Well, we know dr dt, that was mentioned several times. And now if you look back, well, the radius keeps changing, but we have a very specific mention. We want dA dt, but not at any moment, specifically at the moment when the radius is 20. So that allows me to then plug in. We had everything, so I explained again that moment, that r equals 20, was very similar in the previous problem to knowing that the point, that the x was 2 and the y was -1. So we know r is 20, we know dr dt, I plug all that in. I don't even have to solve, dA dt is already isolated. And even looking at the units, we could think logically. If r was in centimeters, area would be in centimeters squared, so the derivative of area would be centimeters squared per second. But notice, if we plug the units in along the way, which I don't think is a great idea. I think a lot of people tend to make little mistakes and goof that up. But if you included it, just look at how it works. 2 pi, r was in centimeters, dr dt was centimeters per second, so I'm still doing all the arithmetic to get the 480 pi, but centimeters times centimeters per second is centimeters squared per second. So even if you include the units, it naturally works out. So what else should we know? If we're going to be able to do more of these problems, what should we know? Well, it's still very similar. It's always, what is the problem describing? And some of these problems talk about volume of, again, a rectangular box. Well, we're going to need the rectangular box formula, the volume formula. If they're talking about something, a lot of the distance scenarios can be made into right triangle situations. My first video, after Dr. Chu's, I do a whole video where I talk about a rocket and a guy standing and the distance as the rocket rises, the distance from the man to the rocket. And I follow that up with a question about the angle changing as the rocket rises. Both of those lead to very natural right triangle situations. The first one, all three sides are a little involved, so we use Pythagorean theorem. The second one talks about angle, so we end up using the appropriate trig function. Dr. Bob makes a video, the first video I post of his, where he's got a ladder that's sliding down a wall. That's another right triangle situation. There's one in the book where they're playing baseball, and there's a runner at first base. Sorry. So we got a baseball diamond. We've got a runner at first base. He starts running for second base, and there's a question about the catcher and his distance to the base runner. Well, initially there's the distance, then there's the distance, then there's the distance, then there's the distance. As the runner keeps moving, even though I've got a whole box here, we're really focused on this side that never changes. This side keeps changing as the runner runs. This side keeps changing as I just keep lining up the distance from the catcher to the runner. So, and if I look in this corner, this is a right angle. So there is a right triangle situation. I could do my a squared plus b squared equals c squared, where these are my sides. This side never changes. This is always from home plate to first base, so that side never changes. That's actually a constant. But this side keeps changing as the runner runs. So the pace that this person runs would be your dB dt. And the way this line keeps changing, that would represent the distance from the catcher to the runner. So we would know this value, and we were asked about the derivative of this side. We'd start off with a squared plus b squared equals c squared. We take the derivative with respect to t, and then we do our best to plug in those other values. So there's still a lot more we could say here. I just definitely wanted to have a video to help connect a few more of the dots that maybe now when you go back and look at the examples in our book, the examples in Dr. Yee's notebook, Dr. Bob's problems, the one I posted, there are a lot to look at. This is a tough section, so you definitely want to try getting some extra experience. And overall, if we need some more, you let me know, and maybe I can make a few more videos guiding us through a few more problems.